Hi guys, welcome to today's video, and in today's video we are going to talk about very special exponential function, and that is e to the x or e to the exponent x. Okay, uh, now uh, I will start this session by saying that uh, this specific exponential function has been created by the calculus. Okay, there is no way that it could have been created by the algebra. Okay, why I am saying that? Because when we are going to construct this function, because in today's session we are going to construct this function, and then we will see that while constructing this function we are going to use lots of limiting steps. Means that something will approach infinity, something will approach zero, and then in the end we will get it. So it comes from calculus. Okay, so I can say that it doesn't come from algebra. Okay, so this is a very special function. Okay, and another reason that makes it very special function is that if you understand this function, you will understand the concept of maximum growth. Okay, here uh, I can write that understanding e to the x means understanding the concept of maximum growth. Okay, now some of you might ask me that is this function different from a to the exponent x? And I would say no. Okay, so this function is similar to a to the exponent x, but this is very special function. Okay, and if you want to understand the concept of maximum growth, then you must study this function. The reason why we are doing it today, because I want you to understand the concept of maximum growth. Okay, or if you understand the concept of maximum growth, it will expand your horizon and you will understand how compounding should work and how it works. Okay, so you will see the power of compounding continuously. Okay, so the very special thing that makes this function very special is that this function slope is same as the function. Okay, what does it mean? Okay, uh, my given function here is equals y equals e to the x, right? Y equals e to the x. This is the function. Okay, the very special thing, or I can say here, the special thing about this is that dy by dx is equal to y. What does it mean? Okay, I have this function y equals e to the x. So the special thing about this function is that if you take the slope of this function, dy by dx, what does it mean? It's a slope, right? So the slope of this is similar as the function. Okay, the slope of this is similar as the function. Okay, what does it mean? It means that slope is same as the height of the function. Now you will realize that that as your x will increase, then slopes get bigger and bigger and bigger and bigger. Okay, so this is one of the reason why this is such a powerful function. Okay, now see here, you can think of any polynomial, any polynomial any polynomial function, for example, x20, x raised to the exponent 100, or x raised to the power 200. This is faster than all these functions. Okay, why? Because it got a special property that its slope is same as the function. Okay, the slope is same as the function, so it means that it will gradually increase and then it skyrocket. Okay, massive growth. Okay, we will see it later. I will give you the real example of how massive growth, or what massive growth means, okay, in terms of banking. Okay, and how what happens when you compound your interest continuously. Okay, we will see that. Okay, so so the very special thing about this function is that its slope is same as that of the function. Okay, now see here, in this session we are going to construct this function, right? So we are going to construct this. Okay, so see here, now this is what? This is a differential equation, right? An equation in the form of dy by dx is a differential equation. This is a very basic differential equation, right? So if it is a differential equation, it must have a start, means we must start from some point, right? So here I will start from x equal 0. Okay, so put x equal 0. Okay, if I put x equal 0, what would happen? Okay, if I put x equal 0, then my y x would be e raised to the power 0, which is 1, right? Or I can write here my yx would be 1, right? Why? Because this is a differential equation, so we must start from somewhere. So I said, okay, let's start from 0. So I set x equals 0. So when x is 0, y becomes e to the 0. E to the 0 is 1. Okay, now this function, okay, now I have yx equals 1, and here I'm writing dy by dx, right? Dy by dx. Okay, for this I will use this blue one for more clarity. Okay, so for slope I'm using dy by dx. Okay, now as the definition of this function says that this is a special function, this is such kind of special function such that that dy by dx, or its slope, is same as the function. Okay, so according to the definition, right, it must be the same, but this is not the slope of this function. right? So what I need to do, so to make slope 1 here, I have to add, to make this slope 1, so here on the top I have to add x, right? Now see here, the slope of dx by dx, right? Now it's 1, right? You got it, right? Now this is 1, it's fine, but now my yx and dy by dx are not same. It means that I cannot stop here, I have to proceed. Okay, so what I will do here, is I have to make it similar to my function yx, right? So here I will write 1 plus x. If I write here 1 plus x, then what would happen? Here I have to write x square by 2. Why? Because when you differentiate it, right, so it's going to be 2x by 2 and x. So see here x, right? So again, what I have to do, I have to make it same, right? Why? Because it says the slope is same as the function. Okay, so here again it's x square by 2. But if I write here, sorry, here I can use the different marker for better clarity. This is 1, this is x, this is x square by 2 by 2. Now here I have x square by 2. Why? Because here it would be, here what would come? Here would come x cube by 6. Why x cube by 6? Why I'm saying this? Because if you differentiate it, it's going to be 3x square by 6, which is going to be x square by 2. See here, x square by 2. Okay, so I hope you get it. Okay, now again I have to make it same, but this 6 can be written as 3 and 2. Right? Now I have to make both of them same because that's what it says, right? So here what I will do, x cube by 3 and here 2, right? So if this comes here, it means here it would be x4 by 24. Why? x4 by 24. Why? Because if you differentiate it, it's going to be 4x cubed by 24, means x cubed by 6. Okay, so here would be x4 by 24, and this thing 24 can be written as 4 multiplied by 3 multiplied by 2. I hope you understand it. Okay, and then the same goes here. Here would be x4 by 4, 3, 2. Okay, and this goes on and on, and here this goes on and on. Here we will get to the point where we will get here xn, right, over n multiplied by n minus 1, n minus 2, and so on, right, up to 1, right? And here what would happen? Here, if it comes here, here would come n times xn minus 1. So here I can write xn minus 1, and that n will cancel, so it would be n minus 1, n minus 2, so on up to 1. Okay, and here plus xn over n minus 1 n minus 2, so on. Okay, now if you look at these things here, I can replace these fraction parts by the factorial, right? Now see here, this is this is this is going to be 0 factorial, this is going to be 0 factorial, this is going to be 1 factorial, this is going to be 2 factorial, this is going to be 3 factorial, this is going to be 4 factorial. 4 factorial. What is 4 factorial? It's 4 times 3 times 2 times 1. I hope you know it, right? And here it's going to be your n factorial, okay? It's going to be your n factorial, okay? So it's going to be your 1, it's going to be your n factorial, okay? I will use here blue. All right, I hope you get it. Okay, the same I will do here. Okay, here I will do the same. Here 1 factorial, here 2 factorial, here would be 3 factorial, 3 factorial, here would be 4 factorial, and here would be n minus 1 factorial, and here would be your n factor, here would be your, here would be xn over n factorial. Now this thing won't stop here, okay? So this thing will go on forever, okay? So here I just put the dot, okay? I hope you can see it, okay? Let me check. Yeah, it's visible, okay? Now both these are same. Why? Because we are just constructing this, okay? So because it's a special property which says that slope is same as the function, okay, for this function, okay? And imagine it's because the slope is same as the height of the function. Now you can just think of the growth, massive, right? So now what we will do here, okay, what we will do here, this is going to be your this is going to be your ex, okay? This is going to be your ex. I can write here ex, okay? So this thing is going to be your ex. This thing is going to be your ex, okay? So this is the construction, okay? We have constructed this, okay? Now just observe few things here, now as we just progress through the series, you can see that our denominator, the fraction part, is getting bigger here. It's massive, okay? And that will make the numerator small, right? So here it will nearly approach 0, but the value cannot be 0, right? Nearly 0, close to 0, okay? So these factorials are so big, the values are so big that the value of overall value is going to be very small, okay? I hope you understand it. And you know, this is one of the reason why this series has a success, okay? I can say that this is one of the most important series. Why? Because if you look at the other series, I hope you know about power series, okay? There is a power series, or we call it geometric series, okay? Power or geometric series that says that your yx is same as, just remove the factorial, part 1 plus x squared plus x cubed plus so on up to xn, and it goes forever. Okay, now imagine when you put here, when your x is small, it's fine, but when it progresses, the value gets bigger and bigger and bigger, and then when you put 1, it will blow. And when your x is more than 1, then it will go crazy, right? And this series has more risk because for values, see here, so x equal to 1 is going to be cut off. But if your value is x greater than 1, this series will fail. Why? Because as you progress to the series, the values get so bigger and bigger and bigger and bigger that this series will eventually fail, right? But if you look at this series is fine for any x, because here your fraction part is so big that the value of the final value is going to be so small. Okay, so I hope you understand it. Okay, so that's why it is one of the most important series. I think after this is one of the most important series. Why? Because this series has a success with all the values of x, okay, whether small, whether big. So this is going to be the savior. Okay, now see here, we have constructed the series. Now we are going to do one thing. Okay, now if you put here, if you put x equals 1 in above series, I mean, which series? This one. Okay, then your e1 is going to be 1 plus 1 plus 1 by 2 plus 1 by 6 plus 1 by 24 plus so on up to up to up to what? 1 by n factorial, right? 1 by n factorial. Okay, now as I have told you that these factorials, their value is going to be bigger. Okay, so the overall value of this is going to be very small. So if you look at it, here we have 1 plus 1 2, and this is 0.5, so 2.5. So when we if you do all the calculation, in the end you will get value of e is 2.71828, and this is your Euler this is your Euler number. Okay, this is your Euler number. Okay, and we can we also call it E constant. Now see here, there is something about this number. You cannot this you cannot represent this number in finite decimal value. This is the approximate value. There is no way that you cannot be represented in finite decimal value. Okay, means that There is no finite decimal value for it. Understand? It goes on and on. Okay, there is no finite decimal value for it, and also this is irrational constant. Irrational constant. What does it mean? You cannot represent this number in the form of P and Q. P over Q, you cannot. Okay, so this is irrational constant. This is a magic number. Why? Okay, now let's come back. What does it mean? Why we call it a magic number? Okay, now I will just say one line here because later on when we are going to implement it in calculating calculating the compound interest, okay, then you will see that this number is going to to make others crazy. Okay, this is a magic number because this is the maximum growth when something grows continuously. This is the maximum growth. Okay, this is the maximum growth. Okay, so I can say here e to the 1 equals 2.71828 represents the maximum growth. Maximum growth. You cannot have growth more than this. Okay, so you will see it later. Why is it that? Okay, but just as now, just put this thing in your mind that this number is very important. Euler's number. It represents maximum growth. Okay, now before we switch, let's talk about the graph of Ex. Okay, so now I can erase this. I can erase this section. Okay, let's talk about the graph of let's talk about the graph. Okay, let's talk about its graph. Graph of this E1. Okay, now see here. Here, this is your X, this is your Y. Okay, this is your X, this is your Y, this is your 1, right? Here, 1, 2, 3, 4, 5. Here, -1, -2, -3, minus so on. Okay, and here, -1, -2, -3, -4, so on. Okay, now see here, because when you put, now see here, this whole thing started when this whole thing started. I've told you that we got the basic differential equation, which means that we have to start from somewhere, and we started at x equals 0. Okay, if you put x equals 0, then it's going to be this, right? Yes or no? If you put x equals 0, then where will you go? If you put x equals 0, if you put here x equals 0, then your yx, right? It's going to be 1. Okay, that's, see here, this whole construction has started from that point. Okay, so at x equals 0, then this is your 1. Okay, 1, and it says that that slope, okay, here the slope is same as the size of function, which means that slope here is same as this height. Okay, so what does it mean? It means it will pass through here and the slope is same as the function. Okay, so now because this is y equals e to the 1. Okay, so this is y equals here. Okay, this is, it will go up, it will go up, and here it will stop because we are doing it for e, right? E raised to the exponent 1. We started here, right? We started here. Okay, we started here. So here it's going to be e1, right? E1, okay, which is 2.71828. Okay, now here on this side, it will follow the same thing. So on this side it will follow the same thing. Okay, because this function started from 0, so y equals 1. Here the slope is going to be 1. So slope 1 means this thing will get bigger. So because this is constructed and this is obtained by putting x equals to 1, so it stops here. Okay, so this is going to be the graph of your Euler's number, right? Yes, you can even construct the graph for this y equals ex, so you don't need to stop here, just go on. Okay, because the slope is going to be the same as the function. So when slope is same as the height of here, it's going to be same as the height of the function. So whatever value it is, that will be your slope. So it means that it's going to skyrocket, right? Because the slope is getting bigger and bigger, right? All right, so just take a note of this thing. Okay, now let's move to the other part. Okay, and just remember this function came from calculus. Okay, it doesn't come from algebra. Now you can see, okay, forgot one thing, that if you have to write this function, sorry, if you have to write ex, okay, and you have to use, because I have said that this function came from calculus and we are going to limit, use lots of limiting here. Something will go to infinity, something will go to 0. So here I can write ex is going to be sigma n goes from 0 to infinity, right? And here it's going to be xn over n factorial. Okay, so I hope this is clear to you. Okay, now let's move to this is a way to write this. Okay, because if you now this thing can be you can break it down into this. Okay, if you put limits, if you declare here the value of n to be that, then you are going to get the same thing. Okay, so it's just a way of writing, but this is the original series. That's how we pack the things. Okay, now come to the example, wonderful example of how this interest works. Okay, now okay, this is your bank. Okay, this is your bank, and here we can have the time frame. Okay, this is t equal to 0, 1 year, 2 year, 3, 4, 5, 6 year, 5 year, 4 year, 3 year. Okay, now see here, we'll start with the with $1. Okay, with $1. Okay, let's say that you go to this bank. Okay, you go to this bank to deposit your $1. $1. Okay, and the bank said that you are welcome to this bank, and if you let your $1 stay in our bank for 1 year, then we are going to give you 100% return. Okay, 100% return. So what does that mean? It means that if I put my $1 here today, $1 here today, then after 1 year, it's going to be $2, right? And after 2 years, because for next year, this is going to be the principal amount. So this will become $4, right? After 3 years, it's going to be $8. After 4 years, it's going to be 60. It's going to be $16, right? After 5 years, it's going to be $32. After 6 years, it's going to be $64. Okay, because every year they are giving you 100%, 100%, 100%, 100%, 100%, 100%. Okay, and as we know, the formula for calculating the formula for calculating this compound interest, it would be principal amount. Yes, principal amount here, 1 plus r, 1 plus r to the power n. Okay, n means the time frame. Okay, now see here, because here my principal starts with 1, so it's going to be this. I hope you understand. Now what's happening here, because I put my $1 in the bank, okay, and then what's the rate of interest? 100%. Okay, so it's going to be 1, right? And how many years? 1 year. So it's going to be 2 after 1 year, right? Understand? Okay, so same, what happened this year? Here becomes 2 principal amount, and here 1 plus 1 plus 1, right? So it's going to be 4 after 2 years, right? Or if you don't want to do that, it's fine. Here you can just put 2 years, right? It's going to be 4. Okay, now see here. Now, what happened is that now if your bank says that what if we compound your interest not yearly but half yearly. Okay, now this is annually. Okay, now they said that okay, we can do it half yearly. Okay, half yearly. Now see here, because here, okay, now I can just draw a chart. Okay, so this is your annually 100%. Because you put in $1, so after with 100% return after a year, it will get $2, right? I hope it made sense. Okay, now the bank said that, okay, we can do one thing now. uh, we can compound it half yearly. Now see here what would happen. Half yearly means that now here this is 1 plus half yearly. Now see here, half yearly means for the first 6 months 50%, then for the next 6 months again 50%. You got my point? So it would be 1 by 2. And how many times they will compound it? 2 times, because it's half yearly. So it's going to be 2, right? And when you solve it, 3 by 2. So the half yearly, this is half yearly. It's going to be almost it's going to be almost $2.25. $2.25, because they did it half yearly. Okay, after 6 months, then after 6 months. Okay, now what if they say that, okay, we are going to do it quarterly? Okay, we are going to compound it quarterly. Okay, quarterly. Okay, now see here, quarterly means this is quarterly. Okay, so for quarterly, what would happen? For quarterly, what would happen? Now this is a equals 1 plus this will become, now see here, quarterly. Okay, quarterly means they are going to do after every, after what, after every 3 months, right? After every 3 months. So what would happen? It's going to be after every 4 months, right? Quarter after every 4 months. So it's going to be 1 by 4, right? Right? Not 1 by 4. They are going to do it quarterly. Yes, 1 by 4. Quarterly. Okay, so here it's going to be 4 times, right? Because you get your interest after 3 months, 3 months, 3 months, and 3 months, right? So it's going to be 5 by 4. Yes, quarterly after 3 months. See here, what would happen? This is 1 by 4 means first 3 months 25%, next 3 months. Now see here, first 3 months 25%, then that principal amount plus interest becomes the new principal amount, then again 25% on that, then you will get a new principal amount, then again 25% on that, then you will get a new principal amount, and then you get 25% on that. So if you calculate all, then it's going to be almost $2.613. It's your quarterly. Okay, quarterly. Now if you say, no, I don't want it quarterly, can you do me a favor? Can you compound it? Can you compound it monthly? Okay, can you compound it monthly? Now see here, for monthly. Okay, now see here, for monthly. For monthly, what would happen? Now monthly, for monthly, 1 plus how many months? 12, right? And here n would be 12 because they will do it every month, right? So if they compound it monthly, so by the end of the year, you will get approximately $2.7146. This is your monthly. Okay, now same. Now you can do it for daily. Okay, if you want, now you can say that, okay, can you please do me a more favor? Can you compound it daily? So here what would happen? 12 multiplied by 30, and here 30. Okay, so if you do all these calculations, then daily would be monthly $2. Oh, sorry. Your quarterly would be 2.44, and then your monthly would be 2.613, and then your daily would be $2.7146. Okay, and now from daily you can say that, can you please do it hourly? Now if you do it hourly, then what would happen? 12 multiplied by 30, 12 multiply by 30 multiply by, because now we are doing it hourly. Okay, so here how many hours? 24. Okay, and here would be 12 multiplied by 30 multiplied by 24. So if you calculate it, it's going to be around hourly, it's going to be around $2.7181. Now you can also, if you can again ask them that, can you please do me the last favor? Can you do it? What? Can you compound it every minute? Okay, so every minute means that here how many hours? 24. Oh, sorry, this is hourly. Then minutes multiplied by 60. So here 60. Okay, so then your minutes, it's going to be $2.71828. Okay, now see here. Now, what if you say that you can do it infinitely? Means that you can compound it continuously for seconds, microseconds, nanoseconds. Okay, so if you do that, what would happen? It would be 1 plus 1 by infinity, and here infinity. Okay, and this is almost E, means this 2.71828. Okay, so what does it mean? It means this is the maximum growth with which your money can grow. This is the maximum growth. Now it cannot grow faster than this. You got the point. Okay, now see here what we are doing here. Okay, fine, we did it for hours, we did it for minutes. Now I just want to do it continuously for seconds, microseconds, nanoseconds. Okay, all the time frames continuously. Okay, then it's going to be E. Okay, so this is the magic number. Now see here, this represents the maximum growth. Okay, now this $1, it's a very small amount. Okay, imagine if here you have $2 million. Okay, then imagine how it would have grown. Okay, so this example is just to show you that how maximum growth looks like. Okay, so I'm sure like this session has just expanded your horizons, because it's really an amazing thing. This is like Euler's number. It's just unbelievable. Okay, so we did this special function e to the x, and from this we have constructed your Euler's number, or e constant. Okay, uh, in the next, because these are the basics, okay, we are going to use all these things when we'll start the logarithm. Okay, so I hope next time we'll get start with your logarithm. Okay, so thank you very much for coming up, and have a great time. Bye bye.